Here's the technical explanation of my function generator and oscilloscope project. Um, First of all, I have this display, LCD display module that uses the I2C protocol to communicate with the microcontroller to display text on there. And then these buttons are handled using external interrupts. So when a button press is detected, then it sends an interrupt to the microcontroller, and that will alter this display and the output peak to peak in frequency for my function generator pin. The function generator itself uses a digital to analog converter, which I set up in my code using this 3.3 volt peak to peak volts. It's just an array of digital values, and those are sent into the digital to analog converter to generate some waveform like that. And then for the oscilloscope portion, it is using analog to digital converters, so it detects this input wave and it samples at a regular frequency to come up with a similar array of digital values, and those are passed through using the USB, using UART protocol into my laptop, and those are displayed here. I have a Python script that goes through and uses those digital values to display them here on a graph. And so when I turn on the function generator, it translates those digital values sent from the microcontroller to this to recreate the analog waveform. And I'll walk through my other code. So here's my function prototypes here. For the LCD display, I have these two functions, the VPP to string and frequency to string, and it looks like a mess. It's just a big switch case statement. I found that was much easier to do than trying to manipulate things into turning it into a string. So it looks messy, but it works. And it takes in a value, one of the peak-to-peak voltage values, and converts that to a string, and then the frequency to string does the same thing for the frequencies. And then inside of the main function, here I set up the LCD display and print out the peak-to-peak and frequency text. And then inside of this update sine wave, I'll go to that. So in here, it stops the DMA, and at the end of it, it starts it again and starts the timer. But it calls these two functions, the generate sine wave and the set trigger frequency, which that changes sine wave. So generate, it takes that initial 3.3 volts array of digital values, and it scales it using the new peak-to-peak value that the user selects. And for all of the calculations, I use the peak-to-peak value scaled by 10. So this 33 represents 3.3, just so that I don't have to work with floating point numbers and I can keep everything as integers. And then the set trigger frequency is also called, and what this does is it changes the frequency that the sample is triggered. So with a greater sampling rate, you're going to have a higher frequency. And so the wave frequency multiplied by the number of samples, which in this case I have 128 samples, that gives you the trigger frequency. And then using this formula, using the internal clock of 80 megahertz, will give me the new auto reload register value, and then it will update that register for a specific frequency. And then also down here is the external interrupt callback function, and this just handles the button presses. So I have the small step, peak to peak, the big step, frequency, small step, big step, and then at the end of the function it will update the sine wave again with the new values. And so in each of these, for each of these pins, it just looks to see if the reverse pin is pressed, then count down, else it will count up. And those values will change depending on if it's the small or the big increments. And same for the frequency, it'll count down or up in different increments. And so the large step for the frequency is just a factor of 10, so it will go up or down in order of magnitude. For the small step, it will go a tenth of that. So if it's at 1k hertz, it will go up to 2k hertz, or if it's at 3 hertz, then it will go down to 2 hertz. And then for the peak to peak, it will count either by 1 volt, so like 2 to 3 or 2 to 1. And then for the small, it will go by 0.1, so like 0.3 to 0.4 or 0.3 to 0.2. And then, so that was the update sine wave, that whole process. And then in my infinite while loop, I have this, this is for the LCD display. It will set the cursor to where the value is actually displayed, and it will convert the peak to peak and frequency values to a string, and then it will write that to the display. Then for the oscilloscope, this is where we start the analog to digital conversion and get those samples, and then it will use this sample value and convert it to a string, how the Python script wants it, in a format that it will understand. And so it converts that, and then it will transmit it using UART over to my laptop for the Python script to interpret. And am I missing anything? These functions I just pulled from one of our labs for the LCD. They're for writing things to the LCD, setting it up, and all of that. And then, oh, here I also, for the buttons, I have a debounce, a way to tell if a button was actually pressed or if it's just bouncing. And so that's what these variables are for, and these checks, it gets the current time and checks if it's a new button press or if it's just bouncing. And so that is all of my code, and that's it for the technical explanation.